If I told you a sugar cube-sized piece of uranium could power your entire city for a day, would you believe me? Sounds like magic, right? But it's simply physics, and it all began 4.5 billion years ago in the heart of a dying star. Somewhere in our galaxy, a giant star 20 times the sun's mass ran out of fuel, collapsed, and exploded. That supernova outshone entire galaxies and forged heavy elements: gold, platinum, and uranium. This stardust scattered across space, later forming our solar system and the rich uranium deposits we mine today. Today, we're literally digging up stardust in the deserts of Kazakhstan or deep in Canadian and Australian mines. But this uranium is no ordinary rock. It holds the potential for fire more powerful than any fuel we've known. Albert Einstein once called enriched uranium the key to the universe's fire. Stay with me, because over the next minutes you'll see how we awaken this sleeping giant, why its double-edged power demands our respect. Natural uranium is mostly uranium-238, 99.3%, while only 0.7% is uranium-235, the magic isotope with the gift of fission. When a neutron strikes a U-235 nucleus, it splits, releasing about 200 million electron volts of energy, over 50 million times the energy from burning a single carbon atom. That split also ejects 2 or 3 neutrons, which can hit other U-235 atoms, creating a self-sustaining chain reaction. This chain reaction, if carefully controlled, becomes a steady heat source. Lose control and it races out of hand. U-238, by contrast, barely fissions and just absorbs neutrons, leaving a pile of natural uranium inert. With too few U-235 atoms, the chain reaction fizzles out. The giant remains asleep. To unleash its power, we must enrich uranium, boost that 0.7% to a level that sustains the fire. Enrichment sounds complex, but imagine a huge bowl of rice where 993 grains are brown and just 7 are fragrant basmati. You want only basmati, so you build a machine to sort grain by grain. That's enrichment at the atomic scale. First, uranium ore is converted into uranium hexafluoride gas, UF6, because gas lets us separate isotopes by weight. U-235 is just under 1% lighter than U-238, a small difference, but enough. We feed UF6 gas into sleek centrifuges spinning at 90,000 revolutions per minute, over 1,000 times faster than your car engine. The heavier U-238 flies to the walls, while lighter U-235 stays nearer the center. We draw off that slightly richer gas as the first step. These machines require stable power grids, ultra-strong materials, and constant precision engineering. One pass through a centrifuge barely raises U-235 from 4.7% to 0.85%. So we link thousands of centrifuges in cascades. Each stage refines the gas further. After months of cascading through stage after stage, the concentration climbs to 3, 4, even 5%. This is low-enriched uranium, or LEU, the fuel that powers nuclear reactors around the world. Next, we turn LEU into ceramic pellets no larger than your fingertip, just 1 centimeter by 1 centimeter, weighing about 7 grams. That tiny pellet packs the energy of 1 ton of coal, 149 gallons of oil, or 17,000 cubic feet of natural gas. Imagine a full truck of coal matched by a pellet you can hold between your fingers. In a reactor core, we stack hundreds of these pellets inside long metal fuel rods. Group rods into assemblies and load the core, millions of pellets in a single reactor. Modern reactors can adjust output to match demand, offering grid stability unmatched by other sources. When U-235 atoms split, the heat boils water, producing steam that spins turbines and drives generators. No carbon dioxide, just pure nuclear fire born of ancient stardust. Today, 440 reactors in 32 countries use this enriched uranium to supply 10% of the world's electricity. In France, nuclear power provides 65% of the grid. In the United States, about 20%. 1 in every 5 homes runs on that silent, continuous energy. This silent power hums beneath our feet, invisible but constant. But what if we push enrichment beyond 5%? What if we don't stop at lighting lamps, but seek to ignite something far darker? Next, we meet the other face of the atom. When we enrich uranium to 20% U-235, it's called highly enriched uranium, or HEU. Push it toward 90% and you cross into bomb territory. Bring two chunks of 90% HEU together quickly to form a critical mass, and in less than a microsecond, a massive chain reaction unleashes a nuclear explosion. The Hiroshima bomb used about 64 kilograms of roughly 80% enriched uranium. Only 1.5% of that fuel actually fissioned, yet it produced the equivalent of 15,000 tons of TNT, obliterating a city. A mere percentage point can mean the difference between lighting homes and leveling cities. Because enrichment technology is the same for power and bombs, the world built safeguards. The International Atomic Energy Agency, the IAEA, acts as the planet's nuclear watchdog. Inspectors and cameras monitor every civilian enrichment plant from Brazil to Japan. They seal centrifuge halls, count every gram of uranium, and track it from mine to reactor to waste. In addition to inspections, the IAEA facilitates technical cooperation and capacity building in developing nations. Under the Nuclear Non-Proliferation Treaty, countries surrender weapons ambitions in exchange for peaceful nuclear aid. This system isn't perfect, but it's why only 9 nations wield nuclear arms, even though 40 could technically build them. But enriched uranium isn't just about power and weapons. In medicine, research reactors fueled by LEU produce molybdenum-99, which decays into technetium-99M. TC-99M enables 40 million nuclear medicine procedures each year: heart scans, cancer detection, bone imaging, saving lives around the globe. Advances in reactor design aim to reduce waste and extend fuel life, maximizing medical isotope production. And in space exploration, when sunlight and solar panels aren't enough, we turn to radioisotope power systems. NASA's Perseverance rover carries a small pellet of plutonium-238 made in reactors running on enriched uranium. As it decays, it produces heat that converts to electricity, powering rovers and probes for decades in the most hostile environments. On Earth, enriched uranium is also a climate ally. Nuclear plants avoid 2 billion tons of CO2 emissions every year, the equivalent of removing 400 million cars from the road. Once built, reactors operate at over 90% capacity for 60 years, delivering clean, reliable baseload power. Solar and wind are vital but intermittent. Nuclear runs day and night, rain or shine. The US Navy recognized this 60 years ago. Aircraft carriers and submarines run for decades on a single fuel load, because uranium is 2 million times more energy dense than gasoline. So here we stand at a crossroads. Enriched uranium is stardust, cosmic legacy hidden in rock. We learned to wake its sleeping giant to spin and concentrate it to unlock a fire no other fuel can match. The atom itself is neutral. It obeys E=mc² without judgment. Whether it illuminates cities, cures disease, powers missions to Mars, or destroys lives, that choice rests with humanity. We hold the pen that writes its story. Will we wield this power responsibly, for progress and peace? Or will we let it cast the longest shadow in human history? This is enriched uranium, the atom that changed everything. If this blew your mind, like, share, and subscribe for more hidden science stories.